Okay, we are discussing about the rocket propulsion. So, in the last lecture we have started writing the equation for the oblique ascent. So, we will continue with that. In the oblique ascent, what does it imply? That I have earth here, and if I fire the rocket along the inclined direction from the vertical. Okay. So, this will imply that the rocket is under oblique ascent. If it is going vertically in this direction, then this will be called vertical ascent. So, we will write the equation for the oblique ascent, but we will continue with the finally, we will continue only with the vertical ascent equation. So, in that context we had the x and y reference chosen, and anywhere we depicted the rocket motion along certain trajectory. So, tangent to the trajectory along this we have the thrust and the v vector, both are acting here. In this direction we showed the drag. So, F drag and F gravity also we showed here in this direction. Okay, gravity will have two components, and one will be the drag component, which is sorry, the drag will have two components, the one along the opposite to the velocity vector, which is called the drag component, another one perpendicular to this is called the lift component. And another for the gravity we have, if this is mg, the weight of the rocket at any time t, then this can be broken into two parts, mg cos theta. So, here theta is this angle is theta, mg cos theta, and this becomes along this direction we have mg sin theta. Okay. So, these are the forces acting on the rocket. So, under this force under these forces, the motion of the rocket along the trajectory we can write as thrust minus F drag minus F gravity is equal to m times dv by dt. Okay. This is along the trajectory. And theta here, this acts as a flight path angle. So, in our case, because as I have told you that as compared to the radius of the earth, the spacecraft will be confined into a very narrow region in which it is being launched. Later on the height may be increased, okay, as in the case of the geosynchronous satellite or the geostationary satellite. Initially they are launched at the perigee position of say 250 to 300 kilometers, and later on the perigee is boosted. So, perigee will be here, but apogee may go high. So, the rocket is really not moving much through the atmospheric stratum, rather it is confined to a very narrow distance from the surface of the earth, and we showed that this is around 5% of the radius of the earth. So, for this case we can assume the flight path angle to be measured from the horizontal that I am showing here. Okay. Otherwise, if you remember for our earlier trajectory transfer or the orbit determination problem we discussed. So, in that case we measured the theta angle, this flight path angle, from the local horizontal. Local horizontal implies if I have this line here. So, local horizontal will be perpendicular to, this is the radius vector here going radially outward. So, local horizontal will be this one, okay, and the flight if the velocity vector is this, then this will be our flight path angle theta. But here for a short range we are measuring the flight path angle with respect to this rather. So, we are not discussing about this, rather we are taking this horizontal here at that place of the launch, and from here we are measuring the theta angle, because it is confined to a very narrow distance from here. Okay. So, in that context the theta angle will be measured with respect to this line, not with respect to the different gravitational line. Moreover, this we are assuming because now we are assuming to be the gravity vector to be the gravitational field to be parallel. So, if the satellite is the rocket is here in this place. So, we are showing this the gravitational force field, it is directed like this. Okay. While if we go in this place, say in this place, so gravitational force field is directed like this, but in a parallel one all of the lines will be parallel directed like this. So, for the short range or short distance, this assumption is also valid. So, we proceed with this and write the equation of motion, but later on we work only for the vertical ascent. Okay. So, this is the equation for oblique ascent. Okay. So, we can write dV equal to m dV, this will be t dt minus f t dt minus f g dt, okay. And dV becomes t by m, and if we integrate it, between V 0 and V. So, T 0 we can assume to start at t equal to 0. Okay. So, from here we can write V minus V 0. Now, this part we have to deal with. So, now we know that T by m dot ISP or we can write it like this, thrust by m dot z, and for that we had put a minus sign before this, okay, because m dot this is a negative quantity. So, minus sign was there. So, thrust divided by m dot z, this we define as a quantity what is called the specific impulse z 0. So, we will write this as, let us say ISP as the specific this is T by minus m dot z 0. Z 0 we have assumed according to the assumption of parallel force field, parallel okay. So, this is the specific impulse and its unit is, as you can check, this is in seconds. So, using the specific impulse, we can write this equation of the dV V minus V 0, this is equal to T divided by m dot z 0. We have put a minus sign here and we multiply by m dot g 0 and then dt here in this place, and this is to be integrated. Similarly, other terms here we have f d by m dt and minus f g by m dt. So, the quantity which is present here, this is we can write as the specific impulse as told earlier. We can take it outside, and here we have the quantity m dot z 0. Okay, and another quantity we have, this is the m which is missing here. So, we put it here in this place. So, this gives us this we can write as dm by dt, and this is z 0 and this is dt by m, and we are putting a minus sign here. So, write the other terms. Okay. So, integrating between time 0 to t, here minus sign we can take it outside, and this becomes I s p times, this can be written as then, and g 0 also we can take out outside, because this is a constant. I s p is also a constant for a particular rocket. This is the specific impulse. Okay, so, the quantity inside the integrand, this becomes d m by m, and now we can integrate it between m 0 to m. And f g obviously we have written as m times g sin theta d dt, and this become divided by m. This is between 0 to t. I s p z 0, integrating this gives us ln m by m 0, here minus sign is there, f t by m. So, similarly we can write for f d also, and here m cancels out, and g we are assuming as a this value as z 0. So, z 0 we can take it outside and write this as sin theta dt. So, delta v we can write as I s p z 0 ln, now minus sign is absorbed here. So, we can write m 0 divided by m. Okay, now, in this equation we will discuss first about this I s p, which is the specific impulse. This unit is in second. So, for different kind of propellants, it is a different values or different ranges are there. So, for solid, rockets, we can have this range from 170 seconds to 220 seconds. For hydrocarbon liquid based rocket, we can have this value from 200 to 350. for H2 and O2, this value can be, this is in seconds, this value can be somewhere around 455. Then we have the nuclear rockets. Okay, somewhere from 300 to 550. Then ion rockets are there. So, this is based on the ejection of the ions, and let us say some 800 seconds. And then we have sorry, for the ion we have 10,000 seconds, 10,000 seconds, and we can have the plasma jet. Plasma jet, this is around 800 seconds. So, for ions we have 10,000 seconds, but later on we will see that. So, it appears from here that let us say using the ion rockets is a very advantageous, but writing the equation as we have written here in this place, and we further work on this. So, in that context we will see that this there are limits. Okay, just having the very high specific impulse does not solve our whole problem. The problem is little more complicated. So, details of this we are not going to discuss. Solid one I have already told you that the solid rockets are based on some solid propellants are used, and they are mixed with some glue and filled into the rocket, okay, and fired by firing a charge. Okay, other ones are little more complicated, and they have their own mechanism. Here we are mostly concerned with the dynamics of this rocket, not with the chemistry of the rockets. So, we avoid that. And the drag force you can write as 1 by 2 rho V a square S times C D. So, this is the drag force basically. This you know from the aerodynamics. So, 1 by 2 rho V a square, this is the dynamic pressure, this is the cross section area. So, that makes it the force term, but this is multiplied by the C D, a coefficient, okay, and then we divide it by m here, and this is our the drag term. So, this is your drag term, gravity term, and this is due to the ejection of the mass. Okay, now, in this format you know that what our objective is. Our objective is to get this delta V sorry delta V maximum. So, we can consider this to be at the burnout. So, we can write here V b minus V 0 indicating the time of the burnout to be T b, okay, and accordingly mass of the rocket at the time of burnout we can show it as m b. Okay, so, m b is the mass at burnout when all the propellants are burnt, okay, and V b is the velocity at burnout. Now, this V b to be or delta V b to be maximum, what is required, that these two quantities should be minimum, okay, because they are subtracting from a positive quantity which is present here. Okay. So, the minimum value of this, the larger will be the change in velocity. this quantity will be minimum, as we can see from here, if theta equal to 0, okay. Or either the time of flight 0 to T b, this becomes small. Okay. So, the gravity term will be minimum when time of flight is minimum and this implies high acceleration from the beginning. Okay, give high acceleration from the beginning. So, your time of flight will be less, or either theta 0 to be 0. So, if theta is 0, then this part vanishes, but it is not possible that theta will be all the time 0. Okay. On the other hand, this is the drag term. So, drag term will be depending on the velocity. The higher the velocity, okay, you can see that the higher the velocity, this is the square of the velocity term. So, higher the velocity, larger will be this drag term. Okay. So, if we accelerate very fast, so the velocity is going very high. So, at that time we will find that this term is becoming high. So, so the two terms are contradictory. This demands that the initial velocity should be very high, so that it passes through the this time of flight becomes small, and therefore, this integrand will become small, while on the other hand this requires that v remains small. So, we have to somewhere optimize this, and this can be done numerically, okay, but not theoretically. So, numerically this can be optimized. So, this is out of scope of this course. And theta equal to 0, what it relates to, like if you are doing the vertical ascent. So, here we are measuring the angle from here, the local horizontal, which is theta. So, this in the vertical ascent theta equal to 90 degree. Besides this, you can see that in the case of the earth, okay, I can have the launch station at the equator, or if our location is away from the equator. So, our launch station will be somewhere away from this, and local vertical will be indicated by this line. And your orbit of injection, obviously, once you are going to inject into the orbit. So, orbit of injection should be inclined, and this inclination is governed by the this latitude at which you are firing the rocket. Now, in this rocket firing, so you can see that because the earth is rotating about its own axis. So, here you have your station is also rotating in a circle, okay, and therefore, it imparts certain initial velocity to the satellite in the inertial reference frame. Okay, just because of the spin or the angular motion of the earth, and this you can write as omega, which is the angular velocity of the earth, and times this distance. So, small r, and this will give you the velocity, which is, now you can see that if you are here in this place. So, this velocity will be tangential to the circle. Okay. So, if you are looking from the top, okay, and your launch station is here. So, this velocity is basically tangential to the surface and it is appearing like this is v 0. Okay. While the rocket launch you are going to do this is the lambda angle as shown here, and this is the center of the earth, this is the center of earth. Okay, and from the center of earth this is the radius vector going outside. So, this is acting as the local vertical, okay, and we can say somewhere the pole is located here. So, the okay, so this is constituting the surface of the earth. Here this is the surface of the earth which is okay. So, this is constituting your surface of the earth. And this forms your this is the center of the earth, and so your equator is somewhere away from this. Figure is not very good. So, we can make another figure here. This is a pole here. So, your station can be located somewhere here in this place. Okay, so, this is your station and this is your local vertical. Okay, assuming the earth to be spherical, okay, otherwise local vertical it differs little bit because of the oblateness of the earth. So, we are just ignoring right now all those things, and this is the north south line, okay, and here your east line will appear here in this place. This is your east line, this is the north line, east line, and this is the north line. Okay, so, launching of the rocket you do along this is the local vertical, while the initial velocity is also present because of the rotation of the earth on its own axis. Okay, you can see that in the east direction, which is your velocity, initial velocity may be present, will be present, and that comes because of the rotational motion of the and if you compute it, it will come around 0.45 kilometer per second. Uh, 0.45 this will be for the around the equator, on the equator, on equator. So, if you have the latitude present here, so this value will differ, okay, as you go toward the pole. So, at this place you can see that there is no velocity present here. So, as you are quite close, as you become close to the equator, this will keep going down, and at exactly at the pole this will be equal to 0. So, this value I have written here on the equator. This is not the exact value, but an approximately this is correct. Okay, so, we are talking about optimizing these terms. So, this can be they are contradictory to each other and they must be numerically sorted out. So, we are not going into the numerical sorting of this, rather we can assume that as the rocket vertically ascends. Okay, so, the atmosphere it becomes rare and rare. So, because the atmosphere is close to the earth, it is a dense, and thereafter the density of the atmosphere it exponentially decays. So, this term can be taken care of ad hocly. Okay, so, this term we can delete it and we can concentrate with only with this term, and this term obviously we see that as we ascend. So, for shorter distance the gravity difference is not much, but still for the vertical ascent at least we can assume this to be theta to be 90 degree and we can work. Okay, so, taking only the first term which is due to the mass, which is this is V 0 minus V b or sorry V b minus V 0 we have written, because on the and we had a negative sign present with this. So, which we have already absorbed inside this. So, it does not matter. V b minus V 0, this quantity is I S p Z 0 ln m 0 by m b. Okay. For the time being, just forget the other terms and look into this. M 0 by m b, this we write as R, and this is called the mass ratio. So, V v is larger at the time of burnout, V v will be larger and V 0 is the initial velocity. So, once we start with this value and we can see from this place that I s p, which is a positive quantity, G 0 is a positive quantity, m 0 is greater than m b. So, this also becomes a positive quantity. So, therefore, V b minus V 0, this is going to be positive. Now, this says that if m 0 is much larger than m b, so your delta V will be larger. So, in general this R, this will be confined to 10, means this mass ratio will be less than 10. Okay. Now, the another thing that you can control, this is the ISP. If the ISP is larger, so you can see that again delta V will be large. So, as in the case of the ion rockets, we wrote that the value of a specific impulse is 10,000 seconds. So, that does not mean that your if you use the ion rockets, your delta V will be very large, because in this case what happens, this one increases. Okay. So, as the specific impulse increases, ISP goes up, R goes down. Okay. This goes up, this goes down. Reason is very simple, that the difference between m 0 and m b is small in the case of the ion rockets. The small mass ejection only takes place. So, therefore, this value goes down while this value is going up. So, if in some way or other both are not satisfied simultaneously. So, somewhere again the compromise is required, and V b we can write as V 0 plus Z 0 I s p ln m 0 by m b, and other terms which are here we have written as delta V gravity, and this is the correction required due to gravity, and delta V due to drag. Okay, and these correction terms are nothing but the terms present here. So, these are the correction terms required. This is due to the drag and this is due to the gravity. So, for the gravity term, at least for this gravity term we saw that if theta is 0, theta remains 0, then this term will vanish, or either the time of flight should be small, where theta is the flight path angle that we have already stated. So, once we go for the vertical ascent, okay, so in the vertical ascent we have the theta, the quantity, this is equal to 90 degree. While in oblique ascent this is not equal to 90 degree initially. So, in the vertical ascent initially theta is equal to 90 degree, and if we assume that the rocket is just vertically ascending throughout. So, we can assume this quantity to be 90 degree throughout. So, in that case just by removing the drag term, we can write this as S p ln m 0 by m b minus z 0 d t 0 to T b. This is for vertical ascent. So, this is not the real situation as we are writing here. This is just to compute that how much velocity is possible if the rocket ascends vertically. So, as you can see this is the earth, and somewhere near the earth you are going to inject the satellite in this orbit. So, if you are starting from this station, okay, so ultimately your velocity vector, you are starting vertically in this direction. So, this will call as the vertical ascent if it ascends throughout vertically, okay. But this has to be bent to inject the satellite. This has to be tilted to inject the satellite into the orbit, because the orbit is this. So, we cannot fire like this and leave it. Okay. This will not put the satellite in the required orbit. So, our orbit is this in which we need to put the satellite. So, the in reality the rocket it ascends vertically, and after ascending it is started it is rotated. So, the its trajectory is tilted, and slowly it is brought closer to the injection point, and at that time it is almost tangential to the injection point, and there it is the satellite is injected, and thereafter it will follow its own trajectory. So, it will follow elliptical trajectory in the beginning, and if it is polar orbit, say the 600 to 700 kilometers altitude, and this is sun synchronous orbit, let us say sun synchronous orbit. Okay. So, then you need to boost up from this 250 kilometers to 700 kilometers. So, perigee boosting is required, and if there is difference in the apogee, so apogee boosting is also will be required. Unlike this, for geostationary satellite, you need a lot of boosting, because here this is 250 kilometers, while the radius of the geosynchronous orbit is around 42,000 kilometers. Okay, geosynchronous. Okay, so, in that case also the boosting is required. So, here our objective is just to calculate the velocity of the rocket if it is just ascending vertically like this. We are not trying to tilt or do any other thing. Okay, so, rocket already we have seen that if the rocket is at the equator, so it will have a component of V 0 which is horizontal, okay, and this value is around, I told it is a 0.45 kilometer around kilometer per second. But this does not add to the vertical velocity. So, while we compute for the vertical velocity, we can assume that the vertical velocity at this point is 0, and then it is ascending directly up. So, the orbit this trajectory tilt is required to inject the satellite into the orbit. Without this, the satellite injection is not possible. Now, we go for the vertical ascent performance of the rocket in vertical ascent. So, from the previous equation, the equation that we have written after removing the drag term, and for the vertical ascent we have put theta is equal to 90 degree throughout, and therefore, sin theta is 1. Okay. So, the sin theta has been taken out of the bracket by putting equal to 1, and we have this quantity. Now, V v minus V 0 then can be written as Z 0 I s p ln m 0 by m b minus G 0 T b. Okay, once we integrate it once more, so we get the y b, the altitude at the burnout. So, y b, this is the altitude at burnout. So, this dV by dt, we integrate this, sorry, this V is given to us. So, V equal to V 0 and plus other terms are there. So, this V will write as dy by dt, okay, and do the integration. So, dy we can integrate it in this way, V 0 dt and plus other terms. So, writing this dy from y 0 to y, and we can put a b to indicate this is the burnout altitude. This will be V 0 from 0 to T v and plus Z 0 I s p ln m 0 by m. So, while we are doing the integration, so in that case m b we are replacing just with m, because m b is the at the termination or when the final burn has taken place. Okay, so, here we will put t equal to 0 and of T b, and the last term remaining with us is z 0 t. So, this becomes g 0 t d t to T b. Okay. So, this equation we have taken here and just written g 0 I s p ln m 0 by m b minus z 0 t. So, this term we are removing, the b we are removing to represent a general condition, and then we are integrating. And this is simple, just write this equation as y b minus y 0, this is equal to v 0 T b plus z 0 I s p. Now, this term requires little more manipulation. Okay. Here we can write this as m 0, m we can write as m 0 plus m dot t. Okay. This is the mass at burnout m dot. We know already that this quantity is negative for a rocket. G 0 t square b by 2. So, we have to further work out this term, and this will give us the altitude at the burnout. Then we write here g 0 t b square divided by 2 sorry. This term we need to first break it out into two portions. This is ln m 0 dt 0 to T b minus 0 to T b ln m 0 plus m dot t dt. Okay, this can be integrated as okay, keeping you know that this kind of integration how do we do ln x dx, if we have to integrate it. So, we assume that there is 1 is present and this is multiplied by ln x and then we integrate it. So, following the same notation, same procedure, we can integrate and write here as ln obviously, here in this case ln m 0, this is a constant. So, we need not worry. Okay, so, this will be simply T b times ln m 0, this can be taken out of the bracket, but this is the general procedure that we will apply to this particular integrand. So, T b times ln m 0 minus t times, and differentiating next time okay, we are assuming here to 1 to be present. So, integrate it. So, this gives you t and this is ln m 0 plus m dot t, and this is to be evaluated between 0 and T b. We will put inside the curly bracket here, and then minus 0 to T b. This is the T term appears here, differential of this term. Okay, so, differential of this term will be 1 by m 0 plus m dot T, and once we differentiate this term. So, here m dot will appear and this is d t, and this is inside the curly bracket and then the bigger bracket closed. Now, you should remember that m 0 m dot, this is a mass ejection rate, mass ejection and this is basically acts as a constant. Okay, for a rocket this is also a constant. So, therefore, this is m 0 plus m dot T b minus zero, and this is the small bracket close. This we are working for this part. Okay. So, once if we put for T b, so T b times m 0 m dot T b, and for 0 this part becomes 0. So, we put here 0 and then again with minus sign we have 0 to T b. Now, m dot m is nothing but m dot T plus m 0. So, m dot can be written as m minus m 0 divided by T. Okay, or either you can say that m dot T is nothing but m minus m 0. So, in this equation this m dot T is present. So, we can replace this in terms of m minus m 0. So, this becomes m minus m 0 divided by m 0 plus m dot T or another way of working with the same thing is this m dot T we can write as m 0 plus m dot T minus m 0. So, you can see that m 0 cancels out, leaving out m dot T. So, if we follow this notation, so in that case this can be written as m dot t and here m 0 plus m dot t minus m 0. So, these two are cancelling out, leaving us with the original term which was present here. So, this notation is little more comfortable, and here you can see that this term and this term, the term this term and this term, they will cancel out. Okay. So, we can divide it and do little more simplification. So, we will carry this term separately. This is inside the curly bracket and then the capital bracket closed. So, work out this term separately, 0 to T b m 0 plus m dot t minus m 0 . Okay, so, this gives us t minus 0 to T b this becomes T b minus m 0 ln m dot and this evaluate at t and T b. So, it is just in a very simple format. So, we can write it as okay. So, we have got the integration of this term. So, next time time is getting over. So, next time we will insert in the original equation and work out rest of the expression. So, this will give us the altitude at altitude reached at the final burnout. Okay, thank you very much. We continue in the next lecture.